my search is looking for leptoquarks, which are a proposed particle which would decay, or basically we'd see them in the detector as a quark and a lepton. We're looking at two different generations, a muon, which a lot of people know, and then a bottom quark. The moral of the story that we did is that using Run 2 data, which is from 2016 to 2018, we were able to put a limit, or we were able to find that these proposed particle leptoquarks, if they exist, that they would have masses above 1800 GeV, which is a significant improvement to previous data.
Today I'm presenting results from the CMS experiment on searches for heavy neutral leptons. Heavy neutral leptons are cruel extensions of the standard model. They explain why neutrinos have a mass, and they can explain dark matter and the matter-antimatter symmetry in the universe. We search for them by using machine learning methods, different techniques for different mass ranges. We have a high mass range where we apply standard techniques trained on different mass ranges. In the low mass range we have long-lived heavy neutral leptons. It means they travel through the detector before they decay and we can see them. So this requires some more specialized machine learning techniques, and the results extend the exclusion region, so we haven't found them yet. But yeah, we are learning more and more about where the new physics could be hidden.
So this poster presents some novel search. The key point is that for any search, you're looking for some signal which looks a lot like some specific backgrounds that are produced in the standard model that everyone knows and loves. For a lot of these backgrounds, we need some simulations to model how many events you'd expect in those specific backgrounds. But the problem is, for signals like the ones in our analysis that look for some distribution in some variable, that variable can be very poorly modeled in background processes that we know exist and we know how they're supposed to be treated. So in this analysis, we derived some novel idea of taking some proxy process that looks like the background for our analysis, and we basically derive some correction factors from data that we know from the CMS detector and everything. And we take those data correction factors and we impose them into the background processes that are important for this analysis, and you can see the distribution gets much better after the correction methods are imposed.
The CMS detector can see some particles like leptons, but can't see other particles like neutrinos. And we use this feature of the detector to search for supersymmetric particles, new possible particles explaining some physics. The idea is that with the particles that we expect, the lepton and neutrino, we have a W boson and lepton flying rather parallel in space, whereas for new particles that can't be seen, the W boson can't be reconstructed that precisely. And that's what we can use to discriminate between our supersymmetry signal against the standard model background. We do a scan over possible masses for these new particles in this plot. And how you read this plot is, you have the masses of the gluino here and the neutralino here, and everything until this solid line is excluded. So we're able to exclude masses up until 2000 GeV, but we can search for new masses, using masses up here.